Hello, today we're going to start a new topics in the chapter of group. So we're going to talk about the concept of subgroup of a group. So we already know about the concept of subset of a set. So similarly here the num suggests that we have a subset and in somehow the subset is a group. So let's go with one by one. So what we have now, so suppose we have a group. So suppose we have a group G with a composition. So G is a group, so G is obviously a non-empty set with a binary composition. So under these compositions it satisfies, so these compositions, but under this composition we have three property. First one is associative. Second property is, so it has an identity elements, not only an identity elements, the identity elements. So has the identity element of the set G under this composition. And third one is each element has an inverse. So for each element we have an inverse. So if G with a binary composition, so it's a binary composition, so it satisfied these three property, then we call the set with this composition a group. So now what happens, suppose we have a subset, so we have a group something like that. So we just draw the graph. So we have a G as a group, and suppose we have a subset something like this. So S, suppose S is a subset of G. Now the question is, when the which type of subset, or when the subset S will be called a subgroup, which means when, so if we have a subset S and we have the same induced composition, so if this is the composition star over here, so under the same composition, if we have the star, the same composition, and under this same composition star, if S become a group, so if S become a group, so what we have a S, a subset of G. S may be equal to G, so S is a subset of G. What we are talking about, so the under the composition in which the group G become a group, and under the same composition star, if S become a group, which means, and this composition star is a binary composition, so it's so let me I am just apologize for my handwriting. So if star is a binary composition, not only a binary composition on the set G, but star is a binary composition on the set S. So this is the first property you have to be. Star have to be a binary composition on the set S, and second condition is the composition have to be also associative, and second condition is it must have the identity elements as the identity elements in S, and the third property is each element of S. So remember that each element of S has an inverse element, so has an inverse. So inverse elements must be an element of S, has an inverse in S. If this property is satisfied, so what we have, so we have a group G star, and S is any subset of G. If suppose under the same induced compositions as the composition of G, S become a group, which means star becomes a binary composition on S. Star is associative and S has an identity elements, and each element of S has an inverse in S, then we call that subset. Not every subset of G becomes a group. So that subset which satisfy this property will be called a subgroup, because we have a subset. So subgroup means actually if you write in English, so it's a subset plus our group. So we have a subset of a set G, and also if we have a group, so it will be a group under the same composition of the composition of G. So same induced composition, it becomes a group, then we will call that subset is a subgroup of the group G. So that's all. Let me give you some example. So before going to the example, so let me erase this first. So here we go. So we have to erase this part. So I am just erasing whole part. So next what we going to do, we give some example. So just here are a few examples, it's always there. So example, so it says that, so example 1, if G star a group is a group, and we know that already any set is a subset of itself. So we know that any set is a subset of itself. So G is a subset of G. So Z is a subset of G. So if we talk in that sense that D is a subset of G, then we can call that G with that same composition is a subgroup of G star itself. So this subgroup is called the improper subgroup of G. So it is called the improper. So the improper subgroup of G. So it's always there. So for any subgroup, itself is a any group G, we have G itself is a subgroup of that group. So is this the improper subgroup of G? So next, it's always there, which is if E is the identity element, A is the identity element. So if is the identity element of G, then the identity B elements with the same composition. So identity element, the set identity elements with the composition. So if we talk about the singleton sets, is a subset of G. So we know that, already know that is a subset of G. So the elements with the singleton set with the same composition of G, if we have the composition star over G, so under the same compositions it's become a group. So it's a subgroup of G. You can check by one just going through all the property of the group, and you can easily check that this will be a subgroup of G. So I just left for you, and do it by yourself. If you fail to do it, just ask me later. So E with the same composition of G is a subgroup of G, and it will be called, so it's the trivial subgroup. So it is called, so this is the name only, so it's called the trivial subgroup. So it's a trivial subgroup of the group G. So all other subgroup, if there is any other subgroup except the improper subgroup and the trivial subgroup, will be called the proper subgroup of G. So let me write that down. So all other subgroup of G except the improper subgroup of G and the trivial subgroup of G will be called the improper subgroup of G. So let me write that down. So if we have a subset H of G, so this does not mean that H cannot be equals to G, but we have imposed something like that. If we have a subset H of G such that H is not equals to Z and H also not equals to the singleton set containing the identity element of the group Z, and if the subset H under the same composition of G become a group, so it's a subgroup. So it's a subgroup of G. If it is a subgroup, the word if is very important. It's not always true that any subset of G will become a group. So H star is a subgroup of G, and this type of subgroup will be called the proper subgroup. So remember the name. So it will be called proper subgroup of the group G. Okay. So now let me give you some concrete example of subgroup. So just let me erase that first. So we have already talked about improper subgroup and trivial subgroup. Now we are talking about the proper subgroup. Now we give you some concrete example. We'll work with that. So just let me erase that first. So I hope you are alright and doing well. So if you have any problem, just comment that below, or you may contact me anyhow. Just ask me the questions, or any teacher you can ask the questions, otherwise you may fail to understand something, and always solve some exercise. So here we go. So sorry for my handwriting again. So here we have example. So what we are talking about, we know that it's from our previous lecture in your class. So we know that the set R of all real numbers with the additions is a group. So is a group. So we know that. So you can easily check that. Also you have already done that. The set of integers plus, we already done that, is also a group. So because the set of integers is a subset of the set of real numbers, so we can say in this way that Z plus is a proper subgroup. So it's a proper subgroup of the group R of real number plus. So this is one of our example of subgroup. So next example will give a subset where it is not a subgroup. So we know that. Now if I talk about, we know that Z plus, Z is the set of integers, Z plus is a group. So we know that already that this is a group. And we also know that the n, the set of all natural numbers. So n is something 1, 2, 3 in this way. So set of all natural numbers. So it's clearly subset of the set Z of all integers. Now I am saying that n with the additions is not a group. Why it is not a group? So you can say that plus, if I going to add two natural numbers a and b, so a and b are natural numbers, say this also becomes a natural number. So plus is a binary comparison. So plus is binary. It's okay, binary. And also you can see that it has no identity element. So there is no such an element. So in this group 0 is the identity element. So for Z plus, 0 is the identity element. So this is the identity element for the group Z plus, but 0 is not in the set and also you can see that there is no another identity element. So n plus has no identity element. So n plus has no identity element. So because it has no identity element, so it's not a subgroup. So no identity element, so n plus is not a subgroup. So we find out an example of a subset which is not a subgroup of a group. So here we have an example. Please remember this example. It's maybe give you some marks in your exam. So next goes to another examples. So just let me erase this part. One more thing I should carefully say to you that this lecture is very important. We're not going to substitute this lecture by coming lecture in our class. So this is the very important to listen these all lectures. So never skip any lectures, otherwise you will be left out from the course. So we're not going to repeat all that thing in your class. So if you have doubt, we can clear that doubt, but we're not going to repeat the whole class. That's the very important thing. So remember each and every lecture. Not only remember, remember is very rough words. So try to understand what I am going to talk, why I am talking over here. So if you have a problem, just consult me or consult any book. So it's the best way to always do some exercise. So it will always clear some doubts. If you have any doubts regarding anything, especially in the subject of mathematics. So let's do some example. So here we have an example. So we know that the set is, if we write the set is as 1 minus 1 I and minus I, and what we know, I is the square, I square is the minus 1, so I is the complex number. So we know that is under the multiplication, so under the multiplications is a group. We already do it over again, and in our class we have done it previously more than one time. So is with the multiplications is a group. So what we're going to do, we will find out is there any subgroup of the group or not. So if I consider the set H, so if we have two elements 1 and minus 1, so is this a group? So let's check. So draw the composition table. 1 minus 1, 1 minus 1, we have the cross. So 1 1 is 1, 1 minus 1 is minus 1, minus 1 and 1. You can see that after the compositions, all elements 1 minus 1 minus 1 1 are from the set H. So cross is binary composition, so composition on H. So it's a binary composition on H. So is there any identity elements? So how to find identity elements? Just is there any row parallel to the upper row, this row parallel to this row? So you can see that this row is a parallel to this row. Is there any column parallel to this column? So yeah, in this column, and the common element will be the identity element. So here 1 is the identity element. So 1 the identity element. So you can easily check that out, that it's obviously an associative. That's, we don't have to go through all that part. So it's clearly going to be associative. Is there inverse elements, each elements? So you can clearly check the inverse of 1 is 1 and inverse 1 minus 1 is minus 1. So inverse. So here we have an element. So if I write element, and if we write inverse over here, so inverse of the element 1 is 1 and minus 1 is minus 1. Why? because if I find the identity element over here, so if I go in the upper direction, also in left direction, so this element has the inverse this element. So we already talked about that in our previous lecture. So 1 has an inverse 1, minus 1 has inverse minus 1. So H become a subgroup. So H cross is a subgroup, of the group of the group is under the multiplication. So it's a subgroup is under the multiplication. Okay.